Hello, how are you? We have seen Newton's universal law of gravity. This describes the gravitational attraction between any two objects with mass. It depends linearly on the masses of each object and is inversely proportional to the square of the distances between these two objects. So, for the same distance, if we replace one object by another twice its mass, the force will be twice as large. But if we keep the masses and increase the distance by 2, the force will decrease by 4. Your weight in a flying airplane will be slightly smaller due to being farther from the center of the Earth than when you are on the surface of the Earth. The acceleration of gravity outside the Earth decreases as 1 over the distance squared. What happens, though, if we go on a journey to the center of the Earth?
It's actually thicker than I thought.
Ladies and gentlemen, I give you the center of the Earth.
Newton's equation F equals gm1 m2 over r squared involves any two objects of masses m1 and m2 at a distance r. In the case of the Earth and you, there are uncountable particles, each one of which has its effect on gravitational attraction. If you are outside the Earth, we can consider as if all the mass of the Earth was at its center and all the mass or your mass will be at your center of mass. About your belly. This is a very good approximation, but what happens when we try to get inside the Earth? Assume we go on a journey at a certain depth, let's say to a distance r1 from the center of the Earth. There we can draw an imaginary sphere with center at the center of the Earth and surface right beneath your feet. The amount of mass enclosed in that sphere will attract you, and that gravitational force will be described with Newton's equation, but with the mass enclosed and the radius of the imaginary sphere. But what about the mass outside the sphere? There is some mass above your head and some mass at the other end of the Earth. Well, it happens that the mass above you pulls you up while the mass on the other end pulls you down. The mass above you is closer, but it is less mass. The mass on the other side is farther from you, but there is more mass. They happen to cancel each other. The symmetry of the sphere makes that for each tiny amount of mass that pulls you one way, there is another amount of mass that pulls you in the opposite way with the exact same force. The mass outside the imaginary sphere does not contribute gravitationally because it cancels overall effect. So, in order to calculate your weight, we only need to consider the mass below your feet, the mass of that imaginary sphere. Now, question. Will you weigh more or less than if you were on the surface of the Earth? Put it another way, what will be the gravitational acceleration at an arbitrary depth inside the Earth? Well, we only need to use Newton's equation for the imaginary sphere. We know that the mass of the Earth is 5.9 times 10 to the 24 kilograms. We calculated that a couple of videos ago. But what is the mass enclosed in that imaginary sphere radius r1? Well, here we need to make some assumptions. We can think that the density of the Earth is constant and then calculate the mass inside of that sphere. If that's the case, first we need to calculate the density of the Earth. Density is equal to mass divided by volume. We know the mass that we calculated before, and we calculate the volume of a sphere of radius 6,370 kilometers. 4/3 of pi r cubed. Now, we divide the mass over the volume and get the density of the Earth. 5,523 kilograms per cubic meter. If this density is constant, then the mass of the smaller sphere is this density multiplied by the smaller volume. 4/3 of pi r sub 1 cube. Now, We have the mass and we have the radius. It is straightforward now to calculate the acceleration you would feel at that depth. Let's assume it is a depth of 5,000 kilometers. Then the mass of the smaller sphere from here the acceleration g sub 1 will be g times m sub 1 over r sub 1 squared (7.72 meters per second). Your weight would be only 77% of your current weight. Let's now do an exercise without numbers. Let's see the power of equation versus numbers. I want to find an expression for the acceleration of gravity g in terms of the depth at which I am, better in terms of the distance to the center of the Earth. Lowercase g is capital G times m over r squared. If the density is constant, then the mass m is density times volume. If the Earth is a sphere, then volume is 4/3 of pi times radius to the third. We can now rearrange this a bit and find that g depends linearly with the distance to the center of the Earth. It decreases as we go deeper and deeper. At the center of the Earth, you would be weightless, as there is no acceleration of gravity there. The Earth pulls you equally in all directions, so there is no net gravitational force at the center of the Earth. Well, if you survive the 6,000 degrees and temperature and more than 3.5 million atmospheres of pressure. This result is true if the density of the Earth was constant, but that is not the case. First, think of the crust of the Earth. There's a big chunk of water there, and the density of water is much less than the density of rocks. The core is denser than the mantle, and the mantle is denser than the crust of the Earth. Actually, what happens if you go inside the Earth is that at the beginning g increases, then it starts to decrease, but that behavior is not linear. You can do a good practice exercise by assuming that the Earth is made of 3 layers: core, mantle, and crust. Use the average densities for these and calculate the gravitational acceleration inside the core, inside the mantle, and inside the crust. You might get some result pretty similar to the actual one. And may science be with you.